Hello, everybody. My name is Gladushev Sergey. I think we are ready to start. I'm a master student of ITMO University, and I will be a chair on these practical classes. I'm glad to introduce Ilia Rasskazov.
Да, слышно. We can hear you.
Well, I think we can start.
Okay, folks. So first of all, a couple of organization questions. Does everybody have Matlab, the access to the Matlab? So does anybody have problems with accessing Matlab? Oh, we have chat. Okay, so as far as I understand, there are two options. One option is that you have Matlab installed on your local machine, on your personal computer. The second option is that you have the access to the Matlab code, Matlab machine due to the remote desktop provided by the organizers. In any event, so let me start with sharing my screen. Okay, so that is basically how the Matlab looks like. So first of all, please find the folder which you have downloaded. And it will be called STRATIFY ITMO. Just find this folder in the Matlab environment. I will give you a couple of seconds to do so. How many people do we have here?
We have many people.
66. You can see it in the panel below. It's participants. It's 66 now.
Okay, 66. Great. So okay. So if anyone will have questions, will be not in our pace. I'll ask Sergey to please check the chat or question and answer section if that is available, and let me know. Okay, so if I will be
Yes,
very
okay.
low or very fast. So okay, so first of all, we download this package from the organizers, from the cloud. It is called STRATIFY ITMO. So in order to everything work correctly, what I'm going to do is just right click on this folder, find add to path, and select selected folders and subfolders. So if I will do this, my gray color folder will become black and will be automatically included to the Matlab environment, which will mean that Matlab will know that we will use all of this folder and all of the functions and subfolders and just everything which is inside here. Okay. So when you do so, for this session, everything will be included in our environment. Before starting to do anything, to launch anything, I would like to briefly describe what's going on in this package and what kind of folders and routines are included here. I suspect and suppose that most of you have more or less experience with, well, if not with the Matlab, but with any other programming language, at least some experience with the coding. If so, it will be not so difficult to understand what's going on in Matlab and how everything is structurized. It's pretty much straightforward here in Matlab. So, okay, I have divided all of the functions and routines into several folders. So first of all, which is very important here and very tricky in Matlab, I have created different functions for calculated Bessel functions. So the trick with the Matlab is that it has only cylindrical built-in Bessel functions. If you would like to calculate spherical Bessel functions, you need to write down your own routines. It's a little bit difficult. It requires some time to make it correctly and carefully. And here I have included all of the Bessel functions which I will need for this package. For calculations of T matrices, if you remember from the lecture. So the name of the function is more or less straightforward. So first letter means if that is D, it will be derivative. If there is no D at the beginning, it's just simply Bessel functions. So S Bessel, S means spherical Bessel function. And the last letter of the name of the function, J, means this is the spherical Bessel function J, if you recall it from the lecture. Spherical Bessel function H, Riccati Bessel function, Riccati Bessel functions J and H, and corresponding derivatives. You don't really need to know everything about how to calculate these functions. They are just needed, and you don't need to care a lot about these functions when you start the scripts. So the color maps folder is just I just put it here because in some of the plots in some scripts I will use a couple of color maps which are not built in the Matlab. It's just for fancy graphs. So the folder DK is for calculating decay rates, which I have explained in the second part of the lecture, in the second lecture. Decay is a function which actually gives us radiative and non-radiative decay rates. So if you open up any of this function, you will find more or less detailed explanation of what's going on here. So first of all, brief description. So for example, decay calculates radiative and non-radiative decay rates of the dipole located inside or outside of a multilayered sphere. Okay. And a brief explanation of what's going on with the input functions, input variables and output variables. And I have tried to do this kind of stuff, this kind of help to every function which you will find in the package. So for any details, for any questions, you can go to each function and consult with this. Also, I have included some references on which papers all of these equations are based. Okay, so decay rates for calculating decay rates. Energy for calculating electromagnetic energy stored within the multilayered sphere. For total energy for electromagnetic energy density, and for different prefactors used in the equations, in the final equations. Next, field. This folder is for the fields, for calculating field characteristics for far fields, which are cross sections: absorption cross section, extinction cross section, scattering cross section. Far fields means that it is for polarized scattering waves S, which are, if you recall from the lecture, are these guys. As parallel and as perpendicular. Also, I have here near fields, the function which calculates near field characteristics for electric and magnetic fields. Here I skip a little bit. So utilities for different useful calculations and pre-calculations needed for the execution of the code. So T matrix for calculating T matrices. I have explained all of them in the first lecture. So again, walk around, you can see carefully everything was going on here. Simple T matrices, composite T matrices, everything is here. So this guy is L convergence. It calculates the maximum angular momentum needed to cut off, to truncate the calculations, and to stop, and which is required for the convergence of the method. Just to give a sense, it has been mentioned here. So how to get L maximum? Where is the cutoff for our summation? And I also have electron free path correction. Again, if you refer to the slides, it's going to be like this. I just amend and change the electric permittivity to a different value. And also I have folder for materials, some tabulated values for silver, aluminum, gold, and silica. So the first two letters denote the material, the second two letters denote from which database they are taken from. So JC is Johnson & Christie, very classic paper for silver, gold, and copper, but I don't have here copper. It's not so difficult to add. Or from different databases, like from MacPeak, Palik, and anything else. So let us start. Let us try to warm up a little bit. So I suggest to go to open folder scripts. These are a number of scripts which we are going to launch today. It's going to see and how does it work. And the most simplest one is, I believe, this one. No, take it back. Okay, this one, test scattering L. I'll give you just a minute or so to find the script. Test scattering L. It is located in folder scripts. I hope everybody have included this folder to the path. Just to remind you that I need to find the whole folder, right click, add to path, and then selected folders and subfolders. Okay, so I have opened the script. Just let me close everything. I have opened script tst sketcher in L. Okay, let me show this guy. And it's pretty much simple. You just press the button run. It will take a little while because I haven't included parallelization to the Matlab. It will take maybe half a minute to initialize the parallel thread for a Matlab. Once it's initialized, it will keep it, and it will keep using parallel calculations throughout our next steps. So if everything was okay, and if you did everything correctly, you should get this kind of a picture. So I would like, again, to give you a moment, maybe a minute, maybe a second. Please write down anybody who has problems. So, okay, guys, how are we doing? Does everybody get the results? Yeah, Dmitry, indeed, you need to add all the folders. So essentially, you will end up with all of the folders and all of the functions inside this stratified mock should be black. Okay, I see. So somebody have very low, very old Matlab versions. So Taif, you have the Matlab 2012. I'm not sure. Yeah, I see that some of the functions, built-in functions in Matlab, have been introduced after the release of 2012. So in this case, I suggest you to use the, if that's possible, remote desktop to the ITMO computers, because it's quite old Matlab version, and it's going to take a while for me right now to fix this problem and to revise the code. So again, if you have if you have versions below 2016A, it's very high probability that it's not going to work. Okay, so yeah, okay, a little slow. That's kind of fine. Okay, it looks like most of the we have more positive results rather than negative. So again, if code is not running, this is the problem of the, you're using quite old Matlab version. I've tried to decrease the version to the lower, so the package to the lower versions, but yeah, try to find out more or less updated Matlab. So, okay, let me now explain a little bit what you have done and what is shown in this figure. So, I hope you see it well. I can just a little bit increase it. So, what we have essentially done here. Okay, let me start, I believe, with the explanation of the script action. So please open up the script and I will go from string to string and explain what's going on here in the script. So first of all, basically this is a description. So the script calculates scattering, absorption, and extinction efficiencies of core shell sphere. I have chosen the gold silica core shell sphere. And also it is interesting to show the contribution of the all of the multipoles which we are calculating. So first of all, what I'm doing here is setting up incident illumination. So when I'm calculating absorption, extinction, and scattering, it doesn't really matter what illumination it is, as long as it is from the outside. So I'm only care right now about the wavelength of the incident illumination. So to whom are more or less familiar with the Matlab, it's going to be easy to understand what's going on here. If not, just very quickly, I'm setting up the array of the wavelengths from 300 to 1500 nanometers, 1 e to minus 9, it's all in meters. And I'm using 1200, 1201 points in this array. So in this case, I'm going to have lambdas wavelengths distributed from 300 to 1500 with a step of 1 nanometer. Here in the next stream, what I'm doing is I'm introducing the multipoles, how many multipoles I would like to calculate. The trick here is that I can use any arbitrary number. So from 1 to 3, from 1 to 5, from 1 to 10, whatever. From 2 to 3, any integer number. So in this case, I'm using from 1 to 3 multiples. Then to set up the particle, what I'm doing here is I'm loading the refractive indices for gold. They're here. So Aurum, Johnson, and Christie. Okay, that is here. I'm loading this data file from my folder. I'm setting up the, and well, basically this, Aurum, Johnson, and Christie. So this file consists of wavelengths. That is the first column. The second column is the real part of the refractive index. The third column is the imaginary part of the refractive index. This is all what I need to know about the material. Wavelength, real part refractive index, imaginary part refractive index. It's kind of standard representation in data files and in digital space. So next, what I'm doing here in the script, I'm setting up the refractive index of silicon. It's constant. I don't need to know the wavelength dependence of the silicon. I'm just setting up it with a constant. Next, what I'm doing here, I'm a little bit doing some trick. I'm interpolating the data from tabulated values for gold, I'm interpolating this data to my lambdas, which I have set. Because tabulated values, they are somehow distributed in terms of wavelength. They're just grabbed from the book, from the paper, a very old paper. And it's not necessarily true that you, in your calculations, you will set up exactly the same lambdas. So I'm using different lambdas, and I'm just interpolating this uploaded data to the lambdas what I have set. Also, what I'm doing here is I need to know the refractive index of the host medium. So in this case, I'm considering the water, and the refractive index of the water is 1.33. That's it. Next, what I'm doing is I'm setting up the particle. To do so, I need to know the radius of each shell, each layer. Here, the first digit is the radius of the core. The second digit is the radius of the shell. This is it. And I'm also setting up the permeabilities. And for golds and or for silica, permeabilities are just unity, just one. That's why I'm setting up the array of ones. Okay. Next, what I'm doing is pretty much simple. I'm setting up output. So I'm allocating the arrays for absorption, extinction, and scattering. So the indices, so these EL, ML, TL, they means that it's going to be electric contribution of the L, so for each given multiple, magnetic contribution for each given multiple, and total one. So for each given multiple, it's very simple. I'm using zeros for, and the zeros and the size of this array is just my numbers of lambdas and numbers of my L's. For total absorption, I don't need the multiples. That is going to be total. I'm just going to summarize everything. So that is why the second dimension is 1. So
Really, we have the question.
Yeah, okay.
The question from Rakhav, and the question, are Johnson and Christie Wallace the accepted standard in the scientific community? There is quite some gap between data from different sources. It's a question about the materials.
Yeah, I see. So, you know, it's it's a very interesting question. So I would say that Johnson and Christie more or less golden standard, and is very well accepted in plasmonics community, and very well reproduce the experimental data. So for alternatives, you can consult with Palik. So I'm just gonna put it into the chat. So Palik database. And if you compare Johnson and Christie and Palik for gold or silver for different materials, it's going to be more or less the same. So what is interesting here is that, well, if you ask, you could consult with the, do you see my screen? Yeah, correct? Yeah. You can see my screen. So you can consult with this paper, and they provide a little bit different constants for metallic materials, which are sort of different from Johnson and Christie in terms of that they can synthesize and they have synthesized and they have measured these properties for metals with lesser losses. Yeah, so what I'm gonna do is just, if you would be interested, just gonna do like this. It's one of the hottest paper in the ACS photonics. One of the most downloaded. Okay, so is that it?
Yes.
Yeah, so nothing. Yeah, new middle length, I think it doesn't matter. So as long, yeah, George and David, I think in terms of running scripts, the difference in performance is not going to be super different. So, okay. I set up the wavelengths, set up the multipoles, set up the refractive indices, set up the particle, the rest of the properties of the particle, like radius and permeabilities. And then allocating the outputs and very, well, maybe not really very simple calculation. So I'm initializing the loop over the wavelengths and construct particle for in terms of refractive indices for each wavelength. Why I'm doing this is because the refractive index of gold is wavelength dependent. So as we can see from here. So different wavelengths, different refractive indices. So because of this, I have to set up the particle again and again with different refractive indices for different wavelengths. And then what I'm doing is, and it is very important here, I'm calculating transfer matrices. Strictly according to the lecture which I have delivered to you. Let me very briefly go to this T-matrix using utilities and T-matrix. So very briefly, it's going to be, so we just allocate wavelengths, size parameters, refractive indices, Bessel functions, allocate some outputs, calculating Bessel functions, calculating transfer matrices, calculating ordered products, or in other words, composite transfer matrices, and end up with pretty much complete picture, complete information about transfer matrices for every boundary, for every composite transfer matrix. And then on using these transfer matrices, I can easily calculate scattering, absorption, and extinction. Again, referring to the lecture. Again, referring to the here. Scattering, easy. Absorption, easy. Extinction, easy. So all of these relations are used in the code. I'm using transfer matrices and getting the scattering, absorption, and extinction efficiency. All of these variables are returned for a single configuration of a sphere at a single wavelength. Then I just put corresponding values in my output and repeat the loop. So in this case, I have a more or less complete picture about absorption, scattering, and extinction for electric and magnetic and total contribution, and for every dipole. Now, and the rest of the stuff is just plotting results. It's a little bit lengthy, but yeah, whatever. So let me see again. So now, given that, we can see different fundamental cross sections, or basically efficiencies, for core shell particle. Absorption, scattering, and extinction. And here I plot contribution of different channels for electric, for magnetic, and this is total. Total is nothing but the summation of all of these curves. Scattering total is summation of these curves, and extinction is summation of these curves. So, any questions so far? Let me double check.
Sorry, I seem to have a question here. You said the graphs below are the summation of the contribution from the three different shells.
From different channels. By channel, I mean electric or magnetic, dipole, quadrupole, octopole.
Okay. And the graph is for the electric field or for the magnetic field? The total.
So the top one is for electric fields. So this is actually the electric components of the absorption, scattering, and extinction, decomposed into the every channel. So in fact, this problem of multiple decomposition will be discussed tomorrow, the day after tomorrow, on this scope. And well, basically, it's all here. It's all here. So scattering, for example, scattering cross-section is nothing but sum of each angular momentum and each electric or magnetic channel. And what I'm doing in graphs, I'm just plotting all of these contributions separately. Why? Because from this picture, I can clearly see that, for example, if in scattering, assume that if you have only this picture, and for scattering efficiency, you have such a plot. And if I ask you a question, this peak, what is the nature of this peak? And if you plot the if you decompose to the different channels, you will immediately see that, for example, this peak corresponds to electric quadrupole, red. And for example, the same can be done for this electric dipole. So these plots are for electric channels and for magnetic channels separately. While the bottom ones, are simply total picture. George Fernandez, yes. Electric for TM, magnetic for TE. So, okay, why magnetic contribution is low compared to electric one? Because we're talking about, so we have here, we have gold particle, plasmonic particle. And essentially, plasmonic particles inherently have a very low, very weak magnetic response. Nanosphere of gold in silicon or water. So it's gold sphere covered with the shell of silica and everything embedded in water. And you can track this from the refractive indices, going from core is the gold, shell is the silicon, and water is the host. And I set up the radius for the core and for the shell. Essentially, this looks like this. Well, without a dipole apparently, but this problem looks like this. And all embedded in water. Okay, let me double check all the questions. Georgi Yermolaev, thank you for the reference. Optics Express, okay, I will take a look on this. If Raghav. So if you decrease the host refractive index to less than 133, I see the broad peak gradually disappearing in the scattering. Any comments on the physical reason? So, well, basically, it looks like the task for everybody. So let's try to do this one. Let's set up the host to the Unity and run the code. And see what's gonna happen. Okay. Well, so in scattering regime, in scattering, what I see? Broad peak gradually disappearing. So I still have a peak. Okay, guys, to distract. So for the scattering regime, we still can see, can observe the peak. It may be not so large. So the nature is of this change is a little bit maybe difficult to explain very simply, but I would rather say if you change the local environments of the nanoparticle, you inherently expect to see how the resonance properties are changed. So right now, let's do the following task. So I'm not gonna show you right now how to do this, but let's switch the materials. So what's gonna happen if calculate the opposite situation. Well, not really opposite, but the inverse situation with the CO2 at our sphere. So try to work on the script. Try to find the place where you need to change something to get the very same results, but for a sphere which has silica core and gold shell, with the very same parameters, like very same radius, same multiple contributions, same wavelengths, so on and so forth. Try to do this. And I will give you a couple of minutes to work on that. So while you are working on this, I'd like to reply to Ramil Minulin. So again, the light source here is just a plane wave. Yes. Essentially, it can be any other wave as long as it is impinging from the outside of the sphere. So, oh, okay, we already have figures. It looks like code works. Very, very nice. I'm very happy. We'll just give a couple of minutes for our attendants. Well, while you're working, I will answer one more question from Kitan Patel. Can Matlab codes can this Matlab code provide an idea of a photonic source based on the nanoparticle size and shape? So again, for surface enhanced Raman spectroscopy, as long as your particle is spherical, and it doesn't really matter how many layers it has. If you calculate the electromagnetic field distribution, well, essentially only electric part, then you find the fourth power of this electric field, and you will immediately have the characteristic of the surface enhanced Raman spectroscopy. So basically, it is related to this slide. Sergey, I have a question for you. So do you see, when I open a chat, do you see it in my shared screen?
Yes, I see your share screen.
The chat. So
the chat?
no. Does it? No. Okay, just, yeah. Just to understand, does it?
No, I see only your slide.
Okay, great. Thank you. Okay, got it. Thank you very much. So, okay. So about Kerker, I'm not really sure about Kerker because, oh my gosh. Okay, so not really sure about Kerker. So let me do the following. So if I would like to change the materials, so let me solve this problem to show how to do this. So if I'd like to use the inverse situation, what I'm doing, what I really need to do is to change the order of refractive indices. And if I do it here, and just cut this, do it here, that's it, done. Okay, so, and that is why you, that is what you is expected to see, these graphs. So here's a very interesting observation from can be made. You see that the peak has been shifted. So extinction is shifted. Extinction scattering, well, absorption was very low because we are talking about pretty large particle, but we have a lot of scattering. So, and this scattering is mostly to the dipole mode. So I have seen comment about strong Kerr effect. Probably Maxime or somebody, I just don't remember the name. So probably this suggestion is related to this observation. It's not really the truth, because Kerr effect is the suppression of backscattering. So while here we are integrating over the whole solid angle. And it's not really the Kerr effect, but rather increased absorption. So here we have a peak in absorption, very small, but big. And this is it. So just particle becomes, well, it doesn't scatter anything, but it absorbs. Yeah. So moreover, what is really interesting here is that our peak has been shifted very much to the infrared region. And this is why these kind of particles, silica covered with gold, aura, are very important for biological applications. Because their spectra, the peak of their spectra, is located in the transparency window of the blood, of the human tissue, of the water, or basically of the water, because water is the main constituent of our body. That's why these kind of particles are very important in biology.
Yeah, we have the question. Don't you forget to change the host apps?
What to change?
Water host material.
Why?
Now your host apps equal 1. Before.
Oh, okay. Yeah. Sure. Whatever. So let us see. Doesn't matter. Oh, a lot of different stuff. So essentially, okay, my idea is still the same. Okay, let it be the water. Still, we have very much shifted to the long wavelength ranges. And it is again very important for biological applications. Okay, so that's how it works for simple fundamental cross sections. Let me show you a bit of more examples. So it's not going to work very well. We are not expecting to see beautiful graphs. So the point here is that let us see how it will look if I have more multiples. For example, if I have from 1 to 5, I can again run the script and essentially confirm that higher order multipoles, so the legend is not updated here, they are very low. So, and what really makes sense is first, second, and sometimes third multiples. Other, I just vanish. Okay, return back everything. So yeah, essentially that's how you get the, again, extinction, absorption, and scheduling efficiencies. I'm going to finally recheck the chat. Let me see very quickly. Yeah, host, yeah, okay. Blood refractive index. Well, I'm not an experimentalist. I didn't measure the blood refractive index, but you know, usually in simulations, if you consider the particles floating within the blood or within human tissue, usually set up the refractive index of the host to be the same as for the water. And in most of these scenarios, it works very well and reproduces experimental data. Okay. Yeah, so for n layers, I'm going to show how does it work for a lot of layers, but in a different example. Yeah, it works for any arbitrary number of layers. So you can just put here, just only be sure that each subsequent radius is larger than the preceding radius. Whatever, put different put the appropriate number of materials. So let me check 1, 2, 3, 4, 5, 1, 2, 3, 4, and one more. And if for refractive indices, for permeabilities, I need to use 6 because, yeah. So right now I have constructed a super multi-layered particle, just for example, just for fun, with some appropriate refractive indices. And if I'm done this correctly, and I've done this correctly, you will see something like this. So for any arbitrary number of layers, any arbitrary number of constituents, you can do this, no limitations. Well, maybe in some numerical performance, in some numerical accuracy, as long as you have super large amounts of layers, but it's going to be fine. Okay, so we are done with this script, which helps us to get fundamental cross sections. If I don't see any questions, yeah, I would go ahead. So I just close this guy. Okay. What I'm doing is, what I would like to show you is this script. Test scheduling FEP. Just I'm gonna give you a minute to open up this script. Okay, I hope everybody found TST SCA FEP. So this script does essentially the same as we have done. So it calculates the scheduling absorption extinction efficiencies for, right now, silica gold core shell sphere. But in this case, we will consider the very thin gold shell, 5 nanometers thick. And here I would like to show you the importance of the of this effect. So, where you have to modify the dielectric permittivity of the bulk sample to take into account the dissipation of the electron and its collision with the boundary of the shell. So to do so, it's so the beginning of the script is pretty much the same. Set up the lambda, loads the refractive index for gold, and I stress here that this refractive index is measured for a bulk sample. Again, we upload the silica, interpolating data. Okay, vacuum host doesn't really matter to show the importance of these finite size effects. And here we set up the particle. So the radius of the core will be 50 nanometers and the radius of the shell will be 55 nanometers, which basically yields in 5 nanometer thick shell. Okay, we set up the output. And here in the loop, it is a little bit different. So par 4 allows me to use all of my cores of my computer. So if you use 4 loop, the Matlab will use only 1 core of your processor. If I use par 4, I will run all of these loops simultaneously. So loops in Matlab is a very big problem, and the performance of loops is very poor. So I just prefer to use par 4. And well, essentially you can just do this, remove par, and everything will be almost the same. Okay. So here I'm introducing yet another trick, yet another opportunity here, just for demonstration purposes. So I'm gonna, so if you see, I didn't set up the cutoff for my multiple number. I'm gonna find my cutoff exclusively for each wavelength, because if you remember, the cutoff L maximum depends on the size parameter, which in turn depends on the wave number, which is the 2 pi over lambda. So, which means that even for a fixed radius of the particle, the size parameter will be different under different illumination. So, for each illumination, so I'm essentially fitting up to this function, that is the L convergence. Here, there's a function which calculates this cutoff. I feed to this function radius, the total radius, refractive index of the host, because I need the wave number in the host. And I'm feeding up lambda. And I'm feeding up the option that I'm going to operate in far fields, because I'm calculating the scattering properties. And then and I consider separately 2 cases. So bulk case, where I use the refractive, where I construct my sphere from, again, silica, bulk, gold, and host medium. Again, calculating transfer matrices, sketching absorption, extinction, and then allocating output. Okay, great. But then what I'm doing is that I'm setting up corrected value for refractive index of gold. I'm using this subroutine, electron-free path. I need the wavelength, I need the initial value, bulk value for the gold, and I need the which is the inner and outer radius of my shell of interest. And also I need some parameters to build up the Judy model. So this function, this string, it corrects the refractive index of gold from bulk sample, which I have uploaded from the Johnson and Creasy database, to correct it according to this equation. Don't be confused, it's very easy. So here are permittivities. In the code is a refractive index. Refractive index is square root of the permittivity, as long as the permeability is unity. So I'm using these equations, and for each given material, gamma and omega p are tabulated values. And to use these tabulated values, okay, I'm using this option. So again, yet another paper from Ordal. Okay, so when I have corrected the refractive index of gold, I'm building up a different core shell particle, where I again have a silicon core, but different shell. So, well, essentially it is gold, it is still gold, but I have taken into account the finite size, the very thin size of this gold shell. And again, I have calculated the transfer matrices, scattering, absorption, extinction, whatever, everything. And again, so let us run the code and see what's going on here. I will give you a moment. Maxime Verger, I don't know. So you're asking about, yeah, valuable for thin films to estimate properly the refractive index thin films. Yes, yes, it can be done. And the point here is that what you need to do and to change here is the effective path. So the effective path. So for thin films, it's going to be simply the thickness of your film. While in the spherical geometry, it's pretty much more involved. Okay, so Dmitry Zhiri. Okay, too many. Okay, Dmitry. So what does that mean? L equals 1 to converge. So Dmitry asked about this string. So from this string, I'm trying to find the, I'm basically not really finding, I'm allocating my multipoles, my angular momenta according to this. So in any case, I'm summarizing all of the contributions. And if in the previous script, we done it from 1 to 3, we just set up the 3 by our own hands. Now, I would like to show that this maximum cutoff can be calculated on using this criterion for far fields. This is this Combi criterion. See these references. And to get this L-conv, well, I'm essentially using this very small subroutine, which looks very much familiar. So I need to cut off my multiples. Zhirichin. Okay, Zhirichin. Thank you very much. So that's pretty much it. So, and if you double check with the variables in your workspace, it may look different on your, I have it on the left side here. So L has been assigned from 1 to 3, essentially. So even I have to do clear all, and again, rerun this script. No. I will not see it because this is part 4. It is not yeah, uploaded. So I suspect there are not so many multiples there. So again, let me return to the figure. Let me return to the figure. And what you can see is we have compared the absorption, scattering, and extinction cross-sections for bulk and corrected permittivities of gold. And we can clearly see that corrected value provides a little bit different results. But sometimes these different results can be very much significant, especially if we are talking about quite small particles. So just for you to play around, I propose to calculate smaller particle. For example, let it be radius 10, so core radius 10, and the outer shell is 15, 10, 15. Oh, okay, so that's basically a very good question. Silver, let's do it for silver. Why not? 10, 15. So if I would like to do it for silver, what I'm doing is I need to upload silver, yeah? So I'm just changing to Argentum, Johnson, Christie. Then I change all of this stuff to Argentum. Well, not very Argentum, double check. And then I also need to check this guy. Argentum. I need silver. So as long as you changed everything for silver and you have, well, set up, for example, different radius, we can go ahead. Let's just clear up our workspace, close our old graphs, and see how it will behave. Wow. So that means that, oh, I know, I just close it. It means that the peak of the spherical particle is a little bit in the shorter wavelength. So I'm going to move my lambda to from 300 to 600 roughly. And run again. Okay, we see it. So I'm going to leave you with this graph. And I'm going to leave it like this. You can see it. So that is the script. I suggest you to play around to see how it works. In the meantime, I will ask some questions. So, would this so Raghav asked, would this free electron path correction give accurate results if some shells were much larger than the free electron path, while others were comparable? So, so look here, it will not make any harm if you introduce this correction to every metallic layer in your multilayered sphere, irrespective of its thickness. Because if thickness will be sufficiently large, then it will be no effect, and nothing's gonna change. If the thickness of some layer will be sufficiently small, then you will definitely see some difference. So in any event, introducing this correction give you confidence that you will end up with much more accurate results for thin shells rather than using bulk dielectric permittivities. So, okay, it works only for, so the very nature of this correction arises from metallic shells. If your multilayered sphere is constructed from gold, silver, copper, aluminum, something else, then you just go to this you go to this slide, you go to this reference, you grab these equations, you find the appropriate values for Fermi velocity, for Drude model, constants for Drude model for your metal. You just put them here and get the corrected result. So in this code, I have tabulated silver and gold. And I believe, let me double check, likely, and aluminum. Yeah, I have, tabulated these values. Gold, silver, aluminum. And I grabbed, drew the model from two different papers, Blabber and Ordal. So the point here is that why different books, why different models? Because they are valid for different frequencies, for different wavelengths. So before using all of this stuff, you need to be very careful and double check with all of this data and how does it fit for your purposes. Simple explanation. So Pavel Trofimov, is there any simple explanation why do LMAX have exactly 3 different conditions and such corresponding X parameters? No, there is no simple explanation. Well, basically, or maybe yes. You know what? Let's see. Let me check. So 3 conditions are for, well, sufficiently small spheres. So size parameter is, yeah, it essentially 0.02 corresponds to Rayleigh regime, and 8, well, sufficiently large, but not as well large. Yeah, so these guys, it's, well, I'll tell you what, that's really huge size parameter. They are, for example, dust in the air, smoke, dust, aerosols. They're usually of this size, these schedulers of this size. And this number 3, it's something fantastic, which you will likely never ever deal with your life, but in the original paper of Wiscombe, he has considered all of these cases. So for what materials generally can this correction be applied? Or can we use this correction for phase change materials in amorphous and crystalline states? Again, metallic nature. So as long as you have a lot of free conducting electrons, you should think about using this correction. Okay, no questions. And finally, just to show that, let's calculate something with a very large shell. So here I still have silver, still have 10 radius of the core, and for example, well, 70, 70, radius 70. If I run this code, I can see that, well, essentially, if the shell is sufficiently thick, I'm just going to do like this, it doesn't matter. Are you using corrected permittivity or not corrected permittivity? So there are no, there is no scattering from the boundaries of your shell. So everything, just both permittivities results in more or less, well, mostly the same curves, mostly the same characteristics. Okay, what time do we end? How many time do we have? How much time do we have?
I think we have 15 minutes. Just 1 second, I check it.
So till 5:20, yeah?
Oh, yes,
Okay.
we finish. Yes, yes.
Okay, till
We have
5.
10 minutes.
Okay, 10 minutes, great. So let me then go next. So now I would like to show you, okay, let's do the following. So TST near field. Yeah, David, exactly. So, well, essentially from the previous script, so if you make the core radius even smaller than 10 nanometers, it doesn't really matter because the silver shell is so thick that it dominates and effectively it behaves like a homogeneous particle. So such a small core radius will not affect your response. Okay, so please open up the TST near field. Yeah, I'm just gonna answer this question. So TST near field. And before we go to the break, I will try to briefly explain what's going on here. So this script, again, it calculates the near fields, near field distribution. Essentially, from the, we're going to reproduce the very same picture from the presentation, this one. We're going to reproduce this picture. It is reproduced. It is a part, all of this data, just for the reference, it is used in this manuscript, pretty good manuscript, I like it. So what we're gonna do is calculate near fields for multi-layered silica gold matryoshkas. So I think if this summer school will be held on offline, if you would go to St. Petersburg at some point of your life, you will find a lot of matryoshkas, and this is the classic Russian toy, a traditional Russian toy, and this is the must-have souvenir from Russia. So keep it in mind. Keep it in mind. And in other words, matryoshkas are just like nested dolls. Nested dolls.
Sorry, Ilia, we have one question from Maxim Vergas. Maybe you see it?
Yeah, thanks. Yeah, I've seen it. Let me
okay.
I'm checking these questions. Yeah, thank you.
Oh, okay.
Yeah, so matryoshkas. So in this case, we're going to use 3 different combinations located here. So silica aurum, silica aurum, silica aurum, silica 6 layers, large and small. of different sizes. Again, upload our room, no, and that is a little bit different. So if I would like to calculate the near field distribution, I need to set up the plane where I would like to get these near fields. And for these particles, I'm setting up the mesh for X and Y coordinates from -70 to 70 nanometers, which is enough, provided that the particle is located at the center of the coordinate system and the radius is maximum radius 50 nanometers. So it's okay. And basically, I'm creating the loop and now the loop is for 3 different combinations. I have 3 different combinations of particles, and loop is for different combinations. What I'm doing here is I'm setting up refractive indices, setting up the permeabilities, calculating again the maximum cutoff for angular momentum, transfer matrices, and from transfer matrices I can get near field distribution, which is again sort of straightforward from the lecture, and plotting results, and this is it. So it's gonna take some time. It is the most complicated calculation to get the near field. So let's try to start this, and while it is calculating, I'm going to answer the question about the cylinders. So what if we replace the spherical shape by a cylinder? You change the spherical Bessel functions to cylindrical Bessel functions. Take care about boundary conditions. Carefully consider transverse electric and transverse magnetic components. Build up these transfer matrices. Set up the illumination in cylindrical coordinates, and you're done. And you essentially can repeat everything. But I have told to do 4 spheres. You can do everything in the same manner, using the very same approach. You can do it for cylinders. And that is going to be very interesting. So the reason why we have chosen spheres, because it's spheres are kind of more popular, more commonly used. Well, at least in that community where I am from, in plasmonics, in photonics, spheres are more common than cylinders. Nonetheless, the cylinder problem is very interesting as well. So it's going to be very interesting to solve it. So if you've done everything correctly, more or less shortly, you can get this picture. Ghulam, hi. We are just about to finish the first part of our practice. So I don't know. So essentially, this script is just to show you that you really can do anything. You can handle any configuration of multilayered spheres and get more or less
Ilia, some problem
results.
with sound.
Yeah, just 1 minute, just 1 minute. Yeah, okay, I know. Okay. So just to show you, I'm just gonna open up the very same paper. These are published results, and they have used, it's not my results, the results from a different group. They have used boundary element method, exact method, but numerical method. They have calculated all of these spheres. And what we have done here, we have reproduced the electric field distribution in the very same spheres? Well, there are a little bit different color maps here, so you could see a little bit very small differences, but quantitatively it's the same. So let's have a break. After the break, we will continue. Play around with the code, think about questions, and see you soon. So, okay, guys, I hope you're back from the break and ready to continue. So while Pavel is trying to fix his computer and fix his connection, let's go on. So so let me a little bit explain again how to use the code. Ghulam Abbas, are you here? Could you just send something to chat? Like plus sign? Are you listening?
Hello, sir.
Yeah, you're here. Okay.
Hello, sir.
So yeah, mute back, and specifically for you and for others, again, I'm gonna briefly explain how to launch this code. So first of all, you need to download the folder, download the package STRATIFY itmo, which has been distributed through this school. Once you have done,
I already have, sir, that. I believe it's with your name, right?
Yes, under my name, yeah. So, okay, very briefly. So you download this package, you click right on this folder, you add to path all the selected folders and subfolders, and essentially you're done. After this, you can run all the scripts. So we have finished with the script which I just realized that I need to share my screen. Okay, now it's great. So what you need to do is, again, download the package, download somewhere, right click, add to path, selected folders and subfolders. Once you did it, it will become black, not gray, like other documents and other folders. You go inside and you go to folder scripts. Essentially, right now we are working on the test near field script, this guy, test near field. So regarding this script, I see the question from the come on. From the Matlab. So the question was how to get these field diagrams in different planes, for example, XZ and YZ. It's very much straightforward. So right now we have distribution of fields in XY plane. Here we can clearly see it. And Z plane is set to 0. For not making the script too much complicated, I set up by default that the plane wave for calculating near fields is incidence with the polarization along X direction, along X-axis. So if you check this in a field, near field, the wave vector is on z-axis and polarization is on x-axis. So keeping this in mind, you now is able to change this mesh as you want. So if you would like to get the field distribution xz direction in xz plane, you just set up the essentially do like this, and you're done. You can calculate them in xz plane. This is it. So you don't need to think too much about this. Just do this. But when you're plotting results, make sure that you're using exactly this coordinate system. Because right now in the script, I have x and y. So if I set up y to 0, then I, in my plots, set z and z. And once you've done this, let me see, it should work. It's gonna take some time. Yeah, so in different plane, it will look like this. But yeah, apparently all of the XY stuff is just moved. This is it. So that's how you can get it, get your field distributions in different planes. This is essentially it. So I'm gonna go back for a while. Okay, so for near fields, again, it is very important. So near fields near field distribution is very important for different applications. For example, surface enhanced Raman spectroscopy. Again, where you have where you need to have large field enhancements to get your Raman signal very large. The point here is that if you can calculate these fields like this, but for some particular cases, they're not so common, but they can be. You can meet them. There is an interest to calculate the averaged fields at some distance, at some radius, maybe within the shell, maybe within a different shell. And you see that the fields are asymmetric, so symmetric, but not centrally symmetric. So because of the plane wave. So, and the problem of calculating the averaged near fields becomes complicated. From one side, you can do all of these, you can average out through all of these points from this graph, but you can do it in way much faster manner. And to do so, I suggest you to open up the test energy density, TST energy DNC. I'm going to give you a minute to find out the script, TST energy DNC. Okay, so what it does is this script calculates electromagnetic density inside and outside of the, again, golds and silica and gold matryoshka. So essentially everything is pretty much the same as in the previous scripts. So you have different wavelengths, you have different radius of your particle, so core, intermediate shell, and the outer shell. You have permeabilities. You load the refractive index for the gold, refractive index for silica. Again, interpolating the refractive index of gold for these wavelengths. Set up here, you can see I'm using the correction for the refractive index of the gold thin shells, because as I have shown you, it's quite important. Here it will be gold core of radius of 10 nanometers, which is small enough to take into account the correction to the permittivity. And again, the thin shell of gold will be between 40 and 45 nanometers. So it will be 5 nanometers thick, which is again pretty thin. So we need to correct our permittivity. Okay, so that is the host. That is refractive index of my matryoshka. So for the energy density, it's very interesting. I can calculate the energy at any particular point of the space, at any distance from the center. So for demonstration purposes, I'm going from the 0 to 60 with some steps. I am preparing the allocating the outputs and then calculating the energy radial density. So here again, I'm creating the loop of the lambdas. I'm trying to find the convergence criteria, calculating transfer matrices, calculating prefactors, some constants required to calculate the energy density, and write down the output. So let us try to run the script together. And see what's gonna happen. So you are expected to see something like this. I'm going to give you minutes to become more or less familiar. And if you don't mind, I need some feedback. Could somebody tell, does it work? Works, not works? In chat, please. Okay, works. Oh, yeah, great, amazing. You're still alive. That's great, guys. That is really hard session today. So what we see from this picture, what we see from this graph? Slow? I don't know why it's slow. Maybe it's slow because we have a lot of different radiuses at which points we calculate the electromagnetic energy density. So what do we see here? So on the y-axis we plot different wavelengths, and here on the x-axis we plot the different position where we record, measure, calculate the electric energy density at different regions of our core shell particle. So here, this from 0 to 10, it corresponds to our core, the golden core, which is clearly see from here. So the radius of the gold core is 10 nanometers. Next, from 10 to 40, we can clearly see the dielectric shell. From 10 to 40, 10 to 40. From 40 to 45, we have a gold shell, outer shell. And from 45 to 60, what I'm doing is calculating the energy density near the sphere. So, and this is it. So essentially, this picture provides you a very comprehensive information about what is going on with the field, with the energy inside and near your particle. And it can be clearly seen that around 750 nanometers. Well, David, yeah, I see your question. Just a minute. That's what I'm going to discuss. So what we see is that around 750 nanometers, the field localizes pretty much intensively. Well, likely because there is a resonance of this sort of structure. Why the electromagnetic energy concentrated in the gold shells? It's pretty simple, because they absorb it. So the energy, the electromagnetic energy is concentrated in shells which absorb energy with higher imaginary refractive index. So the dielectric doesn't truly absorb energy because, well, doesn't sufficiently absorb energy, doesn't significantly absorb energy because the refractive index of silicon here is said to be purely real, 1.45. While for gold, the refractive index is pretty large. The imaginary part of the refractive index is pretty large. So that's why at some point, some resonance, we see a very high concentration of the electromagnetic energy density. Yeah, because of more losses. Yeah, now I see. Yes, more losses. That's right. Let's see. Okay, so essentially this is it about the electromagnetic energy density. So that's how you can get this information. And again, the important thing is that instead of calculating these kind of patterns, in very commonly, you need to get the averaged electric field distribution, And to do so, instead of calculating every point at some distance from the center of the sphere, what you could do is get this expression immediately by using analytic expressions provided in the lecture, somewhere in the lecture. Yeah, by following these expressions. And computationally, it is way much more efficient. And this is it. That's how you do it. Raghav, yeah, So you could use the resonance wavelength to identify the surrounding medium, like a refractive index sensor. Yes, exactly like this. So basically, again, returning back to the lecture, and for example, showing the very last, well, almost last slide. Um, that is the reference too, and that is how the peak is shifted. That is how the peak is shifted due to the change in the refractive index of the surrounding medium. And essentially this work shows that core shell nanoparticles, multilayered nanoparticles, are way much more efficient as a sensor compared to homogeneous particles. They are more sensitive to the environment change. Yeah, Ragav, I have discussed that gold permittivity is taken from Johnson and Christie data. Yes, the plasma frequency of the gold, can be found. Again, very much straightforwardly from these two papers. And here for gold, I'm using not frequency, but the wavelength. Doesn't matter, you can convert it to frequency. For gold from different references, it's either 137 or 144. Abdul Karim, yes, we can do whatever we want. And actually, let's try to do this. So, in fact, just give me a second to understand how to make it more or less easier. Okay, so yeah, David, yeah, let's replace CO2 by silver and see what's gonna happen. And to do so, I propose you guys to take 3-5 minutes, play around with the code and see what's gonna happen if in test energy density, you replace NCO2 with silver. But please be reminded, so you can start playing with this. Please be reminded that first of all, you need to upload the data for silver. Then you need to interpolate the data for silver. And if you wish, or you can suppress this step, you can use the electron free path correction. While you're doing this, it is possible to add anything which you want in this program, in this package, as long as you have data, appropriate data for the refractive index or for permittivity or permeability of your material. You can, if you want, create your own data file or just upload to the workspace these refractive indices, create new variable, whatever you wish, whatever you like. So for the demonstration purposes, the current version of this package contains silver, aluminum, gold, and silicon. The other materials can be used is just whatever you like. So, but for graphene layer, I would be a little bit careful because this is a two-dimensional material. And I'm not really sure and I'm not really confident on how to describe the dielectric permittivity of a graphene layer. If that is a tensor value, this is not a scalar, then you need to derive new equations, you need to solve a little bit different problem, where the generic shell of your multilayered sphere has a tensor permittivity. So that is a little bit tricky. So to summarize, I would say that any material can be used as long as its permittivity is a scalar. And if you're confident that the permittivity is a scalar, then you're fine. So, okay. I'll just give you a couple of more minutes to think how we can replace CO2 layer with Gensum layer, silver layer. Okay, Raghav. So while people are trying to do some calculations, I will answer the question. So have I tried modeling the same schemes using other semi-analytical methods like FDTD? And is there any specific reason for sticking to transfer matrix method? Yeah, this is essentially, there are essentially two reasons. First of all, is the speed. If you use this code, which you're actually using right now, which is based on the analytical solution, you can get the spectra, extinction, absorption, scattering efficiencies. You can get the near-field distribution. You can get the radiative and non-radiative decay rates, which will be considered very shortly, and more characteristics as well. And if you compare the same results, the very same setup, for example, with semi-analytical method, like boundary element method, finite difference time domain method, you will notice, I've done this on the same computer for the very same setups, like very same settings. You can notice the drastic improvement of performance. So if we are talking about calculating just one single sphere, if you're calculating just one single sphere, it doesn't really matter. You can use whatever method if you want. But if you are calculating trying to solve some optimization problems, or you try to get some large picture about different large variety of particles, then FDTD becomes actually good to use. So in this case, I would like to stick to analytical methods, which are very fast and robust. So, okay, a couple of more questions. So, is there any way to calculate the effective refractive index of an array of particles embedded in the medium by using similar codes? Effective refractive index by an array. Yeah, I would. It's a little bit tricky. So Vimala, it essentially depends on the problem which you're considering. So if you consider the regular array of particles, then there are some codes that give you a chance to calculate the reflection, transmission, and other characteristics of the spectra from the regular arrays from particles, from whatever particles, generic particles. And from this information, you can, well, supposedly get the effective refractive index. Well, somehow, yeah. There are some codes, and in fact, for these codes, again, referring to my presentation, I would consult with free software website. And for more info, I would recommend you to go to the wave scheduling website. Every link is clickable. So yeah, you can see that for every link, if you click, you can go to some website. So nonlinear medium, yeah, would be great. Yeah, sure, but it will be a little bit difficult. So for our task, our Argentum layer. So that's how it should look like. So first of all, I need to upload the refractive index for the silver. That's how it looks like. Then what I'm gonna do is I'm gonna use the same procedure to get the to interpolate. I'm gonna use the new variable and interpolate data for Argentum. And for this moment, I'm gonna suppress the corrections for the silver because the intermediate, well, 30 nanometers is quite thick. So I'm gonna suppress this correction right now. And then what I'm gonna do is replace here, instead of NCO2, I'm gonna put NAG, again, and silver. Essentially, this is it. So that's how you replace different material, use different material. And also, for the sake of beauty, I changed the Argentum here in the label. Well, we'll see how it would go. Maybe it work, maybe it's not gonna work. So, okay, guys. And also here, 40, yeah, thanks. It's just very tired already. So here, instead of CO2, I need to put the actual material that I'm using here. Argentum, and so I'm gonna use the database from Portal. And again, clear all. And run the code. Great. So essentially, I have sent this figure from somebody I don't remember, probably David. David, that was you. So David, great. That was great. Let me see other pictures.
Yeah, Ilia, also Maxim sent the correct one.
Yeah. Fedor, Ramil, David, Maxim. Yeah, I've actually already opened the Maxim. Fedor, or you sent the fig file. Okay. Oh my gosh, no. I sent it. It will break down. Okay, Fedor, you probably had the issue with the line 40. Yeah, Fedor, great. Yeah, I didn't mention this explicitly, so that was a tricky one. And yeah, great job, David, that you have noticed this. So that's how you can get different characteristics, and that's how you change the materials You can change the radius, very straightforward. You can do it for different points in the space for within or near multilayered sphere. Different wavelengths, whatever you want. Okay, let's move forward. So now, provided that we can get the energy density, let's calculate the total density, total energy. So total energy is the energy integrated over the whole shell. Georgia, yeah, is not considering the correction for silver shell. So you can add this, but I expect that you will not have very significant difference, because the thickness of silver shell right now will be 30 nanometers. It's not so small. So you can try, but see how it will go. In the meantime, we go forward. TST energy total, test energy total. Here we go. TST energy total. So again, it calculates the total electromagnetic energy within CO2 at our core shell at different wavelengths and different. Well, here I've tried to manipulate and change the core radius, just again for demonstration purposes. So a little briefly to recall that total energy stored within a multilayered sphere is calculated like this. So right now we have plotted the energy density, omega n. These beautiful pictures, these were for omega n. And if you integrate this over R, then you get the total energy stored within each particular shell. And then you can summarize energies within each and every shell and get the total electromagnetic energy stored within your multilayered nanoparticle, multilayered particle. So again, script is very much typical. You can recognize lambdas. Now, okay, I'm starting from the second working stream is a bit different because I'm using different core radius. And I vary the core radius from 10 to 100. So it means that I consider different configurations of the particles. But all of these different configurations will be for the fixed shell thickness. Fixed shell thickness, yeah. So again, uploading database for gold, using the refractive index for silica, refractive index for the host medium. Abdul Karim, no, just only one spherical particle. For multiple spherical particles, I refer you to, again, free software in the web, in the presentation. Then when I allocate refractive indices, I pre-allocate output, and then I calculate total energy. So that's a little bit poking around with the par 4, it's not so significant. For every lambda, I have, I'm looping through different core radius. And then for each configuration, I have for each core radius, the total radii of the multilayered sphere. So the first radius is the core radius, our current core radius, and the total radius of the multilayered sphere is core radius plus shell thickness, which is considered to be fixed. Then you get, again, as it's 5 nanometers, I get the correction. Then I get set up the shell by shell refractive index, core, gold shell, and the host medium. Again, setting up the angular momentum required for the convergence, calculating T matrices. Great. So, as you may have noticed, that in each case, I calculate T matrices and then do some manipulations with them, like I said in the lecture. So it's really important part. So you just get transfer matrix, and from this transfer matrix, you can get anything what you want. Well, as long as you know the appropriate equation. So then I get, again, three factors for different shell materials. And then energy total, that is the function which calculates the energy. So let us, it may take a while to run this code because there are a lot of different configurations here. And I'll tell you what, if you would like to calculate the same stuff by using a finite difference time domain method, it's gonna take a very, very long time. Because effectively, right now I'm calculating 91 different particles. Well, it's not so large. It's not so that big amounts of different configurations, but nonetheless, if you take only one particle in FDTD methods, to get all of this total energy stored within the particle, you will need to get the electric field distribution and then even post-process this electric field distribution to get the total amount of electromagnetic field, electromagnetic energy stored within this multilayered sphere. So yeah, it's taking a little bit while. Oh yeah, angle of incidence. Yeah, it was the question from the lecture. We don't need here the angle of incidence. It's a spherical object. So as long as the spherical object illuminated by a plane wave. So if you change something, it's spherical geometry. Okay, the frequency of incident line is pretty high. Probably this should increase the process time for FTD. Well, maybe. I'm not, I don't work with finite difference time domain methods, but I'm pretty much familiar with times, and yeah, it's gonna take a while for FDTD. So okay, after a while, well, we have different computers. Maybe somebody already have this result. Maybe somebody not. I'm just gonna show you what's going on here. So that is essentially so just to understand, this is really large picture because we have calculated a lot of different wavelengths from 500 to 900 nanometers. And effectively, we have calculated core shell particles with different size of the core, starting from 10 nanometers, it's here, to 100 nanometers. And calculated the energy stored in the core region, so in the entire core. And for all of these configurations, the energy stored within the shell. Yeah, great if it works. It should work. And the energy stored in the shell. And you can immediately see that for small particles, they do not absorb a lot of energy. So absorption, so the energy stored within the particle increases with the increase of the core radius. And also we can clearly observe that most of the energy again is stored in the gold shell rather than in the dielectric core. No. So Jorge Fernandez. So the core again. So if you look to the script, the core we set from 10 to 100 nanometers. So different core radius. But for all of these situations, we put the fixed gold shell, with a thickness of 5 nanometers. So all of these configurations, the one thing is changed here is the radius of the core. And the shell thickness is always the same, the 5 nanometers thickness. Though the inner and the outer radius of the shell, they are apparently different for each of these situations, because in each case, you need to put the 5 nanometer shell on a different core radius. And again, you can clearly see that small particles do not really absorb a lot of energy. Large particles concentrate, they have large energy storage. And the most of the energy is stored within the shell, again, because this is the gold, and the gold has a large imaginary refractive index. That's why it absorbs the energy. Well, again, Abdul Karim. So, how to show this? No, I don't have appropriate figures. So, essentially, again, so in all of the cases, you put this shell, so this is the thickness of the shell, the thickness, and you always put this thickness here. You have the different core radius, but on the top of this core radius, you put always the fixed shell of 5 nanometers. So if you have 20 nanometers core, you do +5, and then it yields 2025. If you have 50 nanometer core, this variable will be 50, 55. So in any case, in any scenario, the outer layer, okay, great. So the outer layer will be larger than the inner. The outer radius of the multilayered sphere will be larger than the radius of the core. So that's about the total energy. Let's move on. Let's now talk about what do we have? We have not so many things to discuss. Okay, decay rates. No, not decay rates. Let me show you the interesting thing about scattering matrices, S matrices. Pavel Trofimov, yes. The field mostly localized in the small layer of aura. Well, essentially, this is the purpose of plasmonics. To localize the energy near or within the metallic shell, sphere, or metallic medium, small metallic nanoparticles. So what we are going to do now, just again, let's clear up our workspace and open up the TSTS. S matrix. So when you open it, I'm going to show you what are we going to do here. So just to remind you that we have talked about the S matrices, and we have talked about the analysis of the eigenmoles of our multilayered spheres by using Weierstrass factorization. And I'm on here. So just to recall a little bit, S matrix can be decomposed as a product of these fractions, where omegas are the eigenfrequencies, and in the denominator you have the frequency of the pole, and in the numerator you have the frequency of the, which corresponds to zero, By the way, somebody asked me about in the lecture about what are we finding zeros of poles for scattering and absorption. And if I find this, just give me a second. Oh, David, that was you. Okay, David, you're a nice guy, it looks like. So for the absorption, we try to get a zero at that frequency such S matrix equals 0. Yes. In fact, like this, for the absorption, we try to find the 0S matrix, like no outgoing waves, just all go to absorption. It's clearly seen that the absorption is maximum if S matrix is 0. And for lasing, when we would like to have the maximum scattering, we are interested in the poles of S matrix. So we would like to have S matrix as large as possible. So, slightly recalled the meaning of the S matrix, and recalling that all of the eigenmodes can be written down in the way that that is the real part and imaginary parts. You can plot them in complex plane and see what is going on there. So, essentially, well, Weierstrass factorization has been proposed quite long ago, but for the purposes of spheres, nanoparticles, multilayered spheres, this approach has been reinvented in 2015. So that is a picture where you can see the scattering matrix. Essentially the only one element for the scattering matrix, which corresponds to the electric dipole. And what's going on here, you plot this S matrix, you just calculate it in a forward manner for some multilayered sphere as a function of the complex frequency. And in this case, you can get some nice distribution, and analyze where you can have, at which frequencies for this exact electric dipole channel, you can have eigenmoles. Basically, Andrei have mentioned that for for one mean coefficient, you may observe a number of poles, and this picture clearly verify this concept. So what we're gonna do is just to reproduce this figure. It's very simple. So on using our transfer matrix approach. So if you read this paper carefully, you can grab all of the parameters. I'm just gonna show you this and boom, go back. So essentially the reference is here in the title of the script. So if you will be interested, you can go and read this. So I set up the illumination. So I'm only interested in the dipole mode here. Okay, why not? So here I will work instead of lambdas I will work in omegas, in frequency domain space. And for omegas, I need to set up the real part of the omega and imaginary part of the omega. And these values are just picked to reproduce again this figure, something like this, in this region, in this range. And also I just set up some points for these regions. Next, I'm straightforwardly, for demonstration purposes, set up the Drude model. So here, that is the trick. Because we're interested in the complex frequencies, it is good for us to get some model, some equation, which we can use to get the electric permittivity. So some function of the frequency. It is different from the tabulated values because they are all are calculated, measured for real wavelengths. And you kind of can do some analytic continuation of these functions to the complex plane, but it's sort of a little bit difficult. So instead, what we're using is using Drude model. So just to recall that Drude model, it looks like this. So epsilon is 1 minus omega plasma divided by omega squared plus I gamma omega. Gamma is the damping constant, so gamma omega p are constants, they're given here, and omega is your frequency. We set up the particle, and the particle is again CO2 core. I don't know, there is a lot of magic about CO2 and gold. They are too much popular in plasmonic community. And the shell, so the core is 120 nanometers and the shell is 150 nanometers. And the shell is gold, described by the Drude model, and the core is again silica. Host medium is vacuum, non-magnetic medium. We pre-allocate our dates for S matrix, and it's just super straightforward. So I'm creating two loops for real and imaginary omegas. So to get the whole space to the whole plane. Then I'm using the Drude model for refractive index. Design my refractive index. So N1 is the silica, N2 is the Drude model for gold, and then H is the vacuum host.
Yeah, there is a question. Sorry.
Just
about the Drude model.
I can. Yeah, Drude model. Yeah. So Drude model. It's kind of, well, essentially, you know what? Interband transitions are very important. Yeah, sure. It's no questions at all. So the whole point of this is to demonstrate this concept. It doesn't mean that it should be precisely like true, precise calculations, but there is only it's only one way to get this picture, to use some analytic equations, analytic models for the refractive index and for permittivity. So here we're using Drude model. So essentially, so this unity can be replaced by another constant to fix these interband transitions, and we will do this a little bit later. So just let me demonstrate how does this work, and I'm going to address this point more carefully. So again, we creating two loops over real omega, imaginary omega, get the complex omega, get refractive index for each shell. Slightly little bit renormalizing lambdas because, well, not really renormalizing, but getting lambdas from omegas. If you read this paper, they have pretty much tricky normalization, but doesn't matter. Then we feed this lambda to the transfer matrix, again to transfer matrices, and then we get S matrix. So you can immediately recognize that it's exactly the same that we have discussed in the presentation, 1 plus 2t, where t is t to 1, 1, 1. So let me recall the presentation. So we get S equals 1 plus 2t, where t to 1 divided by 1, 1. Composite transfer matrices. So it's very much straightforward. You don't need to do any tricks. Just use this theory, get this result. This is the S matrix. Okay, let's run and find out what's going on. I'm pretty sure most of you have already run this code and get some results. It's again not so fast because we're getting a lot of information. Well, while running, I will answer the question from Rahaf. In general, it's every geometry like cylinder, sphere, thin film, they are all good. There is no bad geometry. It really depends on the application, what you're interested in. So yeah, every geometry is good to its own extent, and every geometry can be implemented experimentally. Spheres, cylinders, thin films, some of them easier, some of them more complicated, but yeah, again, it depends on the application. So the whole interest about spheres, because they are these are three-dimensional objects, and they are limited in all three dimensions. So it's a very compact object, and it creates like wow effect if you create a laser, a very small laser, like which size is in all X, Y, Z directions is 20 nanometers. That's just amazing. Compared to other geometries, if you have thin films, for example, they extended in 2 dimensions, and they are finite only in 1 dimension. Or cylinder, it is it's like this, so you are bounded in 2 directions, but in 1 direction, analytics allows you only to find the solution for infinite cylinder. There is only an analytical solution for infinite cylinder. So that's it. So spheres are just interesting because they are too compact. So I'm sharing my screen, and it looks like we have a result. This is the picture of the S matrix, of the elements of the S matrix, which corresponds to the electric dipole contribution. And you can immediately see that poles and zeros of your structure, they are complex conjugated. These are always complex conjugated. So, well, not poles and zeros, but I would rather say that the eigenfrequencies of your system, they are always common pair. Unless you construct bound states in the continuum, then they will go just to the real axis, which we not observe here. And the position of these maxima correspond to the position of the resonances, electric dipole resonances of this structure. And the imaginary part correspond to the decay, so lifetime of this resonance. Something like this. So you can essentially see and make the eigenmode analysis of your structure. And you immediately can see that you expect to have resonances at these frequencies. So here we work in a little bit different domain. These are not lambdas. These are omega divided by omega p. Essentially, I really suspect it will be omega divided by omega naught. Yeah, omega naught. But yeah, whatever. So it's a little bit hard to interpret. So now I would like you, let's do it together actually. So addressing the points of the interband transitions. So in the Julian model, which is given by this equation, so interband transitions can be taken into account by changing this first constant. For gold, it depends on the situation. It depends on which database you're using, which tabulated you're using. I would rather say that it's about from 5 to 10. So you can change this unity from 1 to 10 and then get more reliable results, which will be closer to the real experimental situation. So let's see how it will look like if I will change the constant, which is responsible for interband transition in the Julian model. Yeah, and also Lorentz-Juris can be more suitable. That's for sure. And again, it is very convenient to use this analysis to see what's going on if you have a lot of layers, a lot of different stuff here, and to analyze what's going to happen. So look here, if we change, so if we change the interband transitions, like here, we can see very much different structure of our eigenmodes, which means that indeed the appropriate model for dielectric permittivity plays a crucial role. So here, yeah, I see a very great question from Nitish. So non-Hermitian systems. Oh, that's really great. So what is non-Hermitian system? Non-Hermitian system is that the system, well, let's put it very simply, which has gain. So gain means that, as I mentioned again in the presentation, in the lecture, during the lecture, is that your imaginary part of the refractive index is negative. So something like this. In fact, and what's going to happen in the non-Hermitian system? It's very simple. So we have core. Of silica core, and let's just add some gain here. minus points, okay, minus 0.2, for example. Then multiplied by 1i. That's it. So that's going to be complex. That is a gain. And now let's then see. I'm going to return the to 1, and let's see how it will work. And I propose you to do the same. So change the refractive index of silica core to be the negative imaginary. For example, 0.2. You can change any value. Well, typically it will be from 0 to minus 0.3. That is the typical range. Yeah, just to clarify that non-Hermitian system should contain also, well, both absorption and gain, both losses and gain. And the interplay between these losses and gain will provide you a very interesting phenomenon. So, okay, running. Okay, so now what is happening here is that our pole, they are moving from negative imaginary parts to from the lower complex plane to the upper complex plane, and this is basically the sign of that our system begin acts as a laser. But we have chosen this gain not very smart, just randomly. If at some point you choose gain amount such that this pole will be on the real axis, you will have infinite quality factor of your resonance, because quality factor of the resonance is defined by this equation. So you do real parts divided by imaginary parts, two imaginary parts of your eigenfrequency. And if your eigenmode moves to the real plane, it means that the imaginary part is 0. And if the imaginary part is 0 here, the quality factor just goes to infinity. So if you play around with the gain, you can build the laser. And that's kind of typical procedure. And essentially, you can very clearly observe and analyze the system on this complex frequency plane. So, last but not least, we have 15 minutes. Let's move on. And so the previous system also, why not? So if the previous system also we had a loss, then why we got conjugate pairs? Because this is intrinsic feature. because this is the intrinsic feature of the Hermitian systems. You see that in Hermitian system where there is no gain, poles and zeros, they are all comes as conjugates. Essentially, if you work out this Weierstrass factorization, somewhere here, or maybe not, you see this information. So one more question. Why is sphere so exciting to probe scattering? What about other topologies? About other topologies. What do you mean by topologies, Deepak?
So can we look for some other geometrical?
Other what?
Can we choose some other geometries instead of sphere?
Yeah, of course. You can do any geometry if you want, but the closed form solution is available, well, for a limited number of configurations. So you can do spheroids, you can do stars, triangles, pyramids, whatever you want, whatever you wish for. But in these cases, you need to calculate the exact solution. So you need to do some exact numerical calculations, and the analytic solution is not available for other geometries. Or in other words, the analytical solutions are available for a very limited number of geometries.
Mm-hmm.
And if you have analytical solution, it's a bit easier to understand what's going on there and to analyze what is happening there. Okay, yes. So again, commands complex values. So complex values, frequencies, again. So the real part, basically, this is it's already in the presentation. So the real part is responsible for a position of your, so the actual frequency, the actual wavelength of your resonance. While the imaginary part, the inverse of the imaginary part, is the lifetime of your resonance. So it is responsible to the quality of this resonance. And then the quality factor can be calculated like this. And this is the reason why it is so interesting and important to decompose, to find the eigenfrequencies of your system. Because if you have real and imaginary parts, you do this trick, real divided by 2 imaginary minus, that's it. Then you have the quality factor of this resonance. And you don't calculate scattering, absorption, or you don't do anything. You just find the eigenfrequency. And then from this eigenfrequency, you can have a lot of information about the sphere. David, it's not really, so we consider here an imaginary frequency, so this will make the wave vector also imaginary. Yes, why not? Maybe not. Let me double check. The wave vector. Yeah, you will have the wave vector. Physical. Will also contain the term which configure. Well, it is not so much to be confused about, because we are working in this plane, in complex omega plane, which can be translated to complex K plane, complex wave number, wave vectors plane, and the real situation, so the real life situations will only have place along the real axis where the imaginary part is 0. So other information we should get the scheduling matrix in the complex plane is just the information about the eigenfrequencies to get these results. So, but what you really have in the real life, in real experiments, it corresponds to the, so you just get the graph, the real parts of the eigenfrequency, and that's it. And to the wavelength, I have converted everything to the wavelength here. And also I have the the complex wavelength, and there is no criminal here, completely no criminal, because I'm analyzing the eigenfrequencies. So, okay, last but not least, I would like to move on to calculating decay rates, spontaneous decay rates, normalized radiative and non-radiative decay rates. So please open up the script tstdcy, test decay. Oh, Pavel Trofimov, anapoles. So as Andrei commented on the anapoles, just wait for next lectures. I'm not sure how to comment about anapole states. So open up the tstdcy, and here it will be the final script for today. We have roughly 10 minutes before we finish our very long session. So this script, it calculates decay rates with dipole emitter near or outside or inside the shell of the aurum silica core shell sphere. Again, gold and silica. And to remind you that you can replace all of the materials whatever you wish for, whatever you like for, but be careful, please. So we are going to, well, while I'm talking, I'm just going to run this script, and I recommend you to run this script because it may take a while to perform. So we're going to have, now it's a little bit different, to calculate decay rates at different different wavelengths. Oh, okay, so it's already calculated. Different wavelengths. We are going to use a lot of multipoles, up to 100 multipoles, because, as I have mentioned, for getting the non-radiative decay rates, any arbitrary number of multipole can be excited. So, for the sake of safety, I'm setting up a lot of multipoles. And then I'm going to play with them a little bit later. I'm just going to elaborate on this. So again, uploading refractive indices, pretty much familiar. Setting up the particle 5070 shell, well, core shell. Mu permeabilities. I'm putting the dipole emitter from at different distances, starting from 52 and finalizing in 150. So 52 means that I am located within the silica shell. So I'm not located the dipole inside the gold core. I'm locating it just near the core and moving it within the shell until the 70. And then particle goes further from the multilayered spheres to the water host. Here I'm setting up some constants for the integrations, which integrals which are discussed here. So I need to split the shell, the absorbing shell, to get this integral. I need to split it to some particular number of points. Well, I choose 200. Works pretty well. I can play around with this constant. But also, I'm setting up the accuracy for my decay rates for radiative and non-radiative decay rates. So even though I have a lot of multipoles, my calculation is stops to calculate if the desired accuracy is achieved. So here we get two different cases. In the first case, I fix the wavelength of the dipole emitter and vary the distance according to this variable. And in next calculations, I'm fixing the distance close to the sphere and vary the using different wavelengths of the dipole emitter. So again, here I'm calculating transfer matrices and getting the radiative and non-radiative decay rates. And here, so essentially, I'm not really checking. So the code, the package by itself, checking the desired accuracy, and you set up the accuracy here in 24th string. So here the accuracy, I'm calculating the decay rates to the second digit, which is provided the values of the decay rates is more or less sufficient for the convergence. So again, calculating decay rates for different configurations, different setups, and here's our result. Okay. So now we can observe the following. So here I'm plotting decay rates at a fixed lambda, radiative, perpendicular and parallel orientation of the dipole, and non-radiative. And the thing here is that if the dipole emitter approaches the metallic surface, metallic core, which boundary is located somewhere here around 50 nanometers. And this plot starts from 52 nanometers. The non-radiative decay rates, they significantly increase. They just very rapidly grow. And the reason why is because all of the radiation from the dipole, it goes inside the sphere. Essentially, that's why in all of the fluorescence experiments, in all of the upconversion experiments, you need to separate the dipole emitter and the surface of the metallic core by some dielectric spacer. So look here, if you put the emitter on top of the dielectric, which boundary is located, let me double check, at 70, so our outer shell is 70, that is the boundary of the dielectric outer shell. If you put the dipole emitter here, you can see that the non-radiative decay rates are not as that bad. It means that you can play around with the quantum yield of your system and fluorescence enhancement and so on and so forth. So the whole point is just to understand that the non-radiative decay rates, they very rapidly grow if you approach the metallic surface. And if you fix the distance, here I fix it to 71 nanometers, is just on top of the dielectric surface. You can see the spectral results wavelength results, radiative and non-radiative decay rates. And at some point you see that it is very interesting that radiative decay rates at some resonance, and it's a very long discussion about this. But you can construct this in such a way that radiative and non-radiative decay rates, their wavelengths are separated, which means that you again can construct very effective fluorescence enhancements and quantum U to the dipole emitter in the presence of the metallic sphere. So you can enhance the radiative decay rates, and at the same time, non-radiative decay rates will be not as that bad. And again, if you approach the metallic surface, the situation will be very much different. So there is some trade-off between the radiative and non-radiative decay rates here. So I guess it's a wrap. That's the, we're running out of time. Checking out the questions. Yeah, substrate, yeah, substrate, maybe next year, maybe not next year, maybe sometime next. Alexander is too optimistic about this. So what do you, Manendra, what do you mean by nanocluster? Could you please elaborate in the chat what we can use for nanocluster? Well, decay rates, we are here working with normalized decay rates. So decay rate normalized to the decay rate as if the dipole will emit without the presence of the multilayered sphere. So all of the plots are dimensionless. In the absolute value, yeah, you're correct, David. Okay, so can wait a little bit. So just to remind you, this software that we have discussed is freely available on the internet. So if you recall that it is called STRATIFY, you can simply put the STRATIFY GitLab or STRATIFY Ilia Rasskazov or whatever, just STRATIFY, and it is freely available on the GitLab. I'm gonna throw this link to the chat if you would like to use it. This version, which is on the GitLab, is a little bit more fresh and is adapted to more fresh versions of the Matlab. So if you would like, you can download it, use it for your purposes. If at any point you would like to ask some questions, don't hesitate to contact me or Alexander. Very shortly, all of this presentation will be available for you. Here is my email. Here are some, again, websites. So this is it.
Okay, yeah, thank you very much for your beautiful talk. Thank you for being with us for this 6 hours.
That's crazy.
Yeah. Okay, then if there is no questions, we'll see you tomorrow in the morning.
No, you will not see me.
Okay.
Maybe on the entertainment's program on the Wednesday, but yeah, I'm gonna sleep.
Okay.
Okay, guys. So again, if you will have any questions, please write me to the Telegram chats. Use this EventRock application. I'm very easy to contact, so we'll be happy to talk to you and to maybe collaborate. Thank you very much. Bye-bye, guys.